Okay, so I think we can start. So good afternoon, everyone, and welcome back to our workshop. So in this afternoon, Hanae and I will let you to have hands-on lab session to implement the models we have discussed in the morning session. But first of all, I will introduce a little bit about healthcare dataset design process. So we will begin these sessions with how to understand research questions that we need to answer. And we will talk about the kinds of research questions, what makes of good questions, and a dataset design workflow that get us the answer we seek. We will then explore the different data sources that are typically available in the healthcare system and the types of data available and how those data might be inaccurate in systematic ways. And understanding the mechanism that produce the data we analyze will guide our discussion of the methods for processing those data, as well as how those choices affect the answers to our questions. And in the end, I will also introduce the dataset that we will be using for hands-on lab sessions, okay? So in our discussion, we will refer to this end-to-end procedure as a dataset design workflow, which has 4 steps. And the first and most important one is to pose a research question. And then we identify one or more data sources that can answer the question. And then we will then extract and transform those data into a form needed for the analysis. And then we then conduct the analysis using those data. So after completing these steps, we validate the results and repeat if the process is necessary, okay? So our first dataset design step is formulating the research question. And there are different kinds of research questions. So let's drill down into the types of research questions that can be answered using clinical data. And understanding the kinds of questions is important for us to design our own and to evaluate answers to the question from others. And the types of questions can vary from simple descriptive questions to those that seek a mechanistic explanation. So we will start with the simplest kind of question, which is descriptive. So a descriptive question asks for a summary of the data. So one example is what proportion of the population has familial hypercholesterolemia. So descriptive questions typically involve counts or proportions, okay? And the next kind of question is exploratory. And an exploratory question attempts to find what patterns might exist in the data set available. So exploration involves some analysis or interpretations of the data. So an example is, what are the subtypes of autism using the data at our medical center? And to do this, we could try clustering the data using a variety of sets of features to see what group exists. And then we will need to do additional work to ensure that the grouping we find at one institution is also seen at another place. And the next kind of question is inferential. So an inferential question looks for patterns that go beyond just the particular data set that is available. So the goal is to find generalizable knowledge, but without necessarily identifying the underlying mechanism. So usually this involves assessing how changing the average of one measurement or one quantity and relates to another. So an example is there a relation between gut bacteria and depression in a collection of patients? So note that this is just looking for a reliable pattern. We do not yet know that the pattern reflects any essential mechanism or cause, okay? And the next kind of questions is predictive. So a predictive question looks for quantitative relationships between some features or characteristics and an outcome or event of interest. So the predictions can apply at a level of an individual patient. So an example is, which patients are expected to make extensive use of costly medical resource in the coming year. So predictions are based on reliable association like we saw in the inferential questions, but still do not necessarily reflect underlying causes. Okay. And the next kind of questions is causal. So causal questions looks for the effect of changes in one variable or one quantity on a second one. And a medical question that causal is, for example, for a patient with hypertension and asthma whose type 2 diabetes is uncontrolled with metformin, what is the second best drug? Okay. And the next and final kind of questions is deterministic. So here the question is directly addressing the underlying mechanism. So an example of such a question is, how does androgen deprivation increase dementia rates? So as you can see, there is many kinds of research questions, and having such a grouping allows us to organize our thinking. So in general, clinical data could be relevant to answering any type of research question, but as we will see, clinical data are best suited for answering descriptive, exploratory, inferential, and predictive questions, because answering questions about causality and mechanism is quite difficult. And even with sophisticated methods, such questions often require careful experiments design and collection of new data specifically to answer the questions. And studies who are doing this kind of research question are actually done in a prospective manner. Okay. So we ask these questions mainly to accomplish two primary goals in medicine. First is risk stratification, to decide if to treat a patient. And second, a data-driven selection of how to treat a patient. So knowing the purpose of the questions allows us to figure out if the kind of question we have is adequate, and that the analysis we need to perform in answering it are adequate as well. So we now turn to discussing what makes answering a question useful. So there are several factors that are relevant, and we present this not as a precise formula for some kind of utility measure of the question, but more as a checklist of aspects of a question that we should consider. And sometimes a small change in the question can make it quite useful as well. So first, we should consider how many lives are affected and what is the disease burden of the patients who will be affected by our answer. Okay. And second, what is the chance that the results will have a beneficial effect on the target community? So either the clinicians or the patients. And this is important because not only we want to discover something that is true, but we also want to be able to use that knowledge to improve human health. Okay. And finally, what happens as a result of answering the question? Will this lead to a reduction in death, mortality, morbidity, or other illnesses? Or will it reduce or limit healthcare spending? Or will it increase access to care? And lastly, does knowing the answer help more than one constituent group amongst patients or professionals and payers of care? Because the more people who will be helped, the more allies you will have in implementing your answer. Okay. So we have discussed the 4 steps in a clinical dataset design workflow, and the kinds of research questions and why we ask them, and properties that make the research questions important to answer. So analyzing the record of an individual's journey to answer questions is not easy, but the opportunity is immense. Imagine how a patient experience will change if we could predict risk of specific events to take proactive action, and the doctor will be assisted in the decisions, of what action to take by the past experience of similar patients. But current risk stratification methods are limited in their applicability for a large fraction of patients. And in addition, good evidence for how to treat does not exist for a large majority of clinical situations. So as a result, clinicians have to rely on their personal experience and the collective experience of their colleagues to bridge this gap between available evidence and the needed evidence. But today, It is possible to learn directly from the collective practice of clinicians, spanning the care of millions of patients, and offering an unparalleled opportunity to use large-scale computing and data mining to improve patient care. And as we know, all activities in the healthcare system produce data. So let us review the important types of healthcare data. So first, we need to introduce some terminology. So some healthcare data are structured data of consistent organization. So a table with rows and columns, for example. So a simple example will be a table that contains information about patients, and we could use column for each property of the patients that we want to represent, and such as their medical record number, their age, gender, and lab test results, and so on. And the data for a single patient will occupy one row, and each new patient will get a new row in the table. And note that some data might be missing, so that cell could be filled with a special value to mark this, and usually the code NA is used for this purpose, okay? And also, some data are unstructured, and there are several kinds of unstructured data. So clinical text, images, signals, and so on. So clinical text, for example, although composed out of words, can be quite different from ordinary written language. And some data comes as images, which are large two-dimensional arrays of intensity values, measuring the degree to which some kind of physical energy is transmitted or absorbed by human tissue. And a very common example is a chest X-ray. And sometimes many two-dimensional images are collected together to form representation of volumes. So examples include a computed tomography scan or CT scan and magnetic resonance imaging or MRI. And some data are signals, and these measurements come from a sensor, usually at regularly spaced time intervals. And one common example is the electrocardiogram, which records the electrical activity of the heart using electrodes tapped to the skin near to the heart and hands and feet, and measure often at several hundred times per second. So the key point here is that these textual, image, and signal data lack the regular organization seen in our table example. So we have seen that healthcare data vary along several dimensions, and they occur over different timescales, and they are generated at different points in the patient's care journey, and they have different possible values. And also, they can have different patterns of missing values. So remember that there is an inherent time ordering to all the different data types that are generated for particular patients at various places in the healthcare ecosystem. And knowing this timeline view of the data is essential for effectively using the data, okay? So our workshop hands-on lab session will focus primarily on using the record of routine clinical practice to improve healthcare, because the data we want to use are collected for other purposes, which is to deliver care, and are collected as a byproduct of that care delivery. So these data are called observational data and are used as referred to as secondary use. So observational data have some important strengths, but also have some significant weaknesses. So first, let's look at the strengths. So observational data in healthcare are typically very large. There might be millions or even billions of records. And this is a great advantage because we can expect to see some occurrences of even rare events. And also, like observational data are created during the routine operation of the healthcare system. And this makes them valuable in studying real-world utilization. And because observational data are usually created for some other primary purpose, so they are available for a search and the secondary use at relatively low additional cost and without long delays and after provisioning of the service. And so accessing them can be efficient and they can be updated in straightforward ways. And lastly, because the dataset are used by multiple parties, they are not subject to rapid changes in format, and the format may even be standardized over time. Okay. However, observational datasets have some weaknesses. First, those data are static, and it may be difficult to obtain additional features or details needed for particular analysis or questions. And also, patient records may be spread across multiple sources, and connecting all of them together so that all of the patient record for given patients appear in one place may be a difficult problem. So connecting sources together so that all of the relevant data for given patients appear in one place, called record linkage, is sometimes a difficult problem. But note that the difficulty varies widely across countries, because some countries use a single personal identifier, which makes linkage very easy. And some countries have a single integrated healthcare system in which all the records may already be linked. So the third one is observational data creation and collection are usually not designed to facilitate research or secondary analysis. And therefore, this data can be imperfect and biased and may require significant cleanup. So observational data may be biased because of where the collection process is located in the healthcare system and because of incentive and changes in medical practice. And therefore, while appearing useful, they can be of uncertain and various quality. Okay. And lastly, the medical record captures encounters with the healthcare system, not the patient's state of health over time. That can be incomplete coverage of the patient journey over time. So the medical record will be missing information about self-treatment or what happened before symptoms became apparent. So given these properties of observational data, we can see that there are many advantages of using this data, but at the same time, there are some limitations that cannot be ignored, okay? So we have discussed the different types of clinical data, their strengths and weaknesses, as well as the sources of biases and errors. And we now turn to the sources of this dataset. So the medical record of a patient used to be paper sheets bound together into a folder called a chart. And therefore, we still refer to medical records as charts, but they are now mainly stored in computer systems. And these are the electronic medical records, or an EMR. And sometimes they are also called the electronic health record, or an EHR. So these data are collected in the hospital and clinic and contain patient demographic information, such as name, their sex, and date of birth, along with diagnosis and procedure codes, clinical notes, medication administration records, imaging, and lab test results. So an example of widely available electronic medical record dataset is the Medical Information Mart for Intensive Care, or MIMIC, which is part of the project PhysioNet. And this is the dataset that we will use later on, okay? So it contains data on patients in the critical care units of Beth Israel Deaconess Medical Center in Boston. And as of the year 2020, this dataset holds the records on about 38,000 patients. And another example of medical record data is Cerner Health Facts, which is a commercially available database of medical records for multiple facilities. So now I want to introduce the dataset that we'll use during the hands-on lab session. So it is sourced from MIMIC and was created for the purpose of a case study in the book titled Secondary Analysis of Electronic Health Records. So it contains about a total of 46 variables, including demographics, clinical observation during the first day of ICU stay, and the outcomes, okay? And for this hands-on lab session, the research question that we would like to answer is, which patients are expected to have worse prognosis in terms of mortality following their ICU stay? And as we have discussed before, this type of research questions belongs to the predictive research question, okay? And these are the input variables and the labels that we are going to use to build and validate the model. So you might not be familiar with the variable names, but well, you do not need to know every single variable here. And if you want to know the definition of each variable, you can always refer to the website here. So basically the input variable contains data about patients' demographics like age, gender, and their previous diagnosis, like did they have a stroke or respiratory diseases before, and also some relevant lab test results like their white blood cell, hemoglobin, platelet levels, all are measured at the first day of the ICU stay. So many of these inputs clinically are correlated with patient prognosis. For example, a patient who has a very high white blood cells level would indicate that the patient is suffering from serious infections and may have poor prognosis. And for the label, we choose this variable as the label. And this variable means that within 28 days, which can be in the hospital or outside the hospital following the ICU stay. Okay. And its values are binary, one for yes and 0 for no. Okay. So before building the machine learning models, we need to first divide our data set into different subsets. And there are two possibilities here, either to divide the dataset into two subsets, namely training and test sets, or if our machine learning models have some hyperparameters that need to be fine-tuned, then we can choose to split the dataset into three subsets: training, validation, and test sets. So for example, when we develop a support vector machine model, there's a hyperparameter called learning rate that we need to fine-tune, right? And for this case, then we need validation set. And based on the model performance on the validation set, then we can choose the most appropriate learning rate. So why we need the test train split? So the objective is so that we can accurately evaluate our machine learning models, because we do not want our machine learning models to only perform well on our dataset, right? And we also want the models to hopefully perform well on other data that the models do not see during the training process. So we need to divide them into these three subsets. So first is a train set, which contains the actual data set that we use to train the models, meaning that the models sees and learns from this data. Okay. And the second one is validation set, which is used to evaluate a given model, but this is for frequent evaluation. So we use this often to fine-tune the model hyperparameters. And hence, the model occasionally sees this data, but never it does learn from this, okay? So we use the validation set results and update higher level hyperparameters, okay? And the last one is test set, which provides the gold standard used to evaluate the models. And it is only used once a model is completely trained using the train and validation sets. So the test set is generally well curated. It contains carefully sampled data that spans the various classes that the model will face when used in the real world, okay? So now that we know what these sets do, so we might be looking for recommendations on how to split our dataset into train, validation, and test sets. So usually an 80-20 or 70-30% train test split is considered reasonable, where 70 to 80% of the data is used for training and validation, and the rest is used for testing the model performance. But this mainly depends on two things. So first, the total number of samples in our data, and second, the actual model we are training. So some models need substantial data to train upon. So in this case, we will optimize for the larger training sets. And models with very few hyperparameters will be easy to validate and tune. So we can probably reduce the size of our validation set. But if our model has many hyperparameters, then we want to have a large validation set as well, okay? And also, if we happen to have a model with no hyperparameters, then we probably do not need a validation set too, okay? But all in all, a test set is kind of compulsory because it gives us information about how our model performs on data that the models never have seen on the training process, okay? And another method for shuffling the training and testing data is something called cross-validation or K-fold cross-validation. And this is very similar conceptually to a train test split, but instead of just creating one split, we essentially do this multiple times. So more specifically, we split our data set into K subsets or K folds, and then train on K minus one of them. And what we are doing is holding out the last one of the subset to use as a test set, okay? And when we do this over and over, we can get many estimations of the model on a variety of test sets or subsamples of the data. And this can be very advantage when there is not much data to begin with. Okay, so now hopefully you are familiar with the dataset we're going to use, and that is the end of my session. Is there any question to ask? If not, then next is your turn to build the models and you'll be guided by Hanae. Okay. So Hanae, it's yours.
Okay, thank you, Ronald, for introducing those concepts and the data set we're going to focus on. So now we plan to create some tutorials so that you can have a more practical sense of how to implement those models in practice. So I'll share with you Collab tutorial. It's read mode only. So what you should do is click on this link, please, and then copy this tutorial, this file on your own, create a copy to copy it on your own Google Drive. Okay, and I'll try to share my screen so that you can, okay. So I'll give you some time to do that. Share this. Okay. So normally you should be able to see my screen. Basically, when you open the tutorial, you can put file and say save a copy in Drive. So you should do that. Otherwise, you won't be able, normally if the link works, you won't be able to edit the file. Okay. So save your own copy. Okay, and okay, could you please put some like yes or no answer in the chat box whether you manage to open the link correctly and copy it in your Drive, please? Or whether you have issues, do not hesitate to raise hands. Okay. Oh, can you copy the link? Can you, so you cannot see the link? Okay, I share it again. You're welcome. So I'll give you some time to do it. Please let me know once you've done copying it on your own Drive. And meanwhile, I just introduce a bit about the Collab. I don't know if you're familiar with it or not, or you already use it. So Collab is actually it's a resource so by Google. that gives you access from your drive. You can access some cloud computing resources. So, which means basically you have some computing resources that are not localized on your computer, but on Google's servers. And it's quite intuitive to use it. You only need your browser and to connect to your drive to open a Collab session, etc. And so it's quite convenient, and also it's free. At least you have some free version of it. And another thing which is quite convenient is that you don't need to install anything on your own desktop. You can install it directly in your virtual machine furnished by given by Google. So that's quite convenient. However, I just want to raise the fact that it comes with some privacy and security drawback issues. So if you use this resource in your research, maybe just check which data you're using and what are the privacy sharing authorization for those data sets, because every data you put on those Collab will be accessible by Google, basically. So especially if you work on some medical data set, make sure you have authorization to do it. So for instance, here, Ronald and I, we picked a data set which is publicly available, so that's no big issue. So don't put sensitive data there. And yes, basically. Okay, so I see that some people managed to open and create a copy. Is it okay for everyone? It's just that otherwise you won't be able to try things on your own. So if someone has a problem, please let me know. Okay. Okay, and so, okay, so meanwhile, maybe people are finishing copying, etc. I just so start with some environment setup. So I try to explain as detailedly as I can. I am aware that maybe this tutorial will be a bit boring for those of you who already have a strong experience with Python, with machine learning problem solving already. Maybe it will be a bit too long for those who have absolutely no experience. So yeah, I hope it will be okay in both cases. So the idea, so what I shared with you is the tutorial without with a blank cells to fill, so you can write the code yourself. And what I'm sharing with you now is the one with some suggested answers. So in case you don't find the answer by yourself. So about the introduction of a data set. So Ronald already gave us a good sense of what the data set is about. And also he discussed about the question we can answer in this context, right? So which is a more predictive research question about whether we can determine whether a patient will survive in ICU after 28 days. So first, what we need to do with Collab is some environment setup. Here I put you the list of main software libraries we are going to use. It's Python libraries. And so some links to the documentation, so you can browse it. They are very well documented, so you can browse it and look at examples, copy some code that are very can be applied to a lot of settings. So this tutorial is all done in Python. So for those who are not familiar, try to explain as much as I can. Basically, programming in Python is quite intuitive if you have other programming experience in other languages. So first thing you want to do is to click on this first cell in order to import the useful libraries for the rest of the tutorial and install them if they are not installed by default in Collab. So yeah, so here, for instance, in my case, it was already downloaded. Hope you can all do it. Should take not too long. And then we will add a seed value to fix a seed value. So basically, I wanted to introduce this because in practice for your research or other projects, personal projects, research projects can be quite useful and life-saving. So it's to fix a seed value for, so fix a seed value. Does someone know why we need some seed value? What is it, etc.? Anyone has any idea about that? No? Have you ever used something similar? Yes, thanks, Genshi. Yes, so you say to make results same. Yes, so it's good for reproducibility because as you may think from this morning, there are a lot of steps in machine learning where you can have some randomness in your training, etc. And in the split of a data set, etc., you can pick samples randomly. And then that means that you can have the exact same data set and the exact same model architecture, the exact same optimization algorithm, etc., and still end up with different results because it will depend on the initialization, the data split, etc. So here we introduce some seed value for the different libraries. So you can just run the cell basically. But the idea here is that we can, yes, all have the same split, etc. And so it's good when you share a code with someone else, but also for your own code when you do some research. You maybe at one point you want to fix something so that you can publish and people can reproduce. Yeah. So that's the idea. So you set a seed value, and then for different libraries, we can seed this. Okay, next one is set up your working directory in Collab. So here you can run the cell too, but just maybe make sure. I think you should remove this this last working directory. I mean, you should put here the link to your current working directory. So if you just copied the Collab into your main drive, you just remove the text I highlighted. Just change to your directory. Basically, this will this will like add the content of your Google Drive, like the stored data, close to the notebook, so that you can share the data, etc. Okay. So maybe does anyone has issues with at this point? Did everyone manage to do that? So I have a question. Is it possible to automatically assign the seed value for every library? I think so. I'm not too sure. Here I wanted to be sure, so I just put this value and repeated it for all libraries. Not too sure you can do this. You mean Andre do like set a value for each library in like one line of code? That's what you mean? I'm not too sure about this. That's why I did more more lines of code. It may be possible. I should check online. Welcome. Okay, so I hope everyone managed to get the data set and the Collab ready. So now what we're going to do in part one is to do database preparation. So first download the datasets that we just talked about. So basically with this cell, you'll be able to download the dataset from the website directly. Okay. So this is the open publicly available dataset. So it's not huge. So it's more like a toy dataset that we can play with and try different models with it without having the problem of time of computing, size of the dataset, etc. Because you see here it's good. Maybe you can see here. You have in Collab how you use your memory, your so active memory and your disk. So if you have a huge dataset, then you will fill this very, very quickly, basically. So that's why Collab is useful, but not in all settings. If you have a huge genomics, like for instance, I work on genomics data, and I cannot use Collab to do any analysis. Okay. So once you downloaded it, the first thing we want to do. So here you can see it prints all the files that were downloaded from this folder, online folder, a license, the data dictionary, which will describe the data, just some annotation of what variables are, the full data, etc. And so here, first thing we want to do is to read this data table. So remember, like Ronald just said, showed you, and as I also introduced this morning, we want to have this table, like blue table of data set describing your patients with your features. And so one very useful way to do that in Python is to use pandas, which is very close to our data frame in R. So you can do this. And then so, yeah, one quick question maybe is like, once you have this data set loaded, created, maybe you can try to use some of the pandas function to observe, to look at the size of the data set, of this toy data set. How many variables are they? How many patients are they? And maybe you can display the few first lines to see how it looks like, to check that you don't have an empty data frame. So yeah, if you can maybe also answer in the chat what you found when you about the dataset size. Any idea? Any results? I'm sure some of you have are very familiar with those kind of function already. Ah, have an error. Yes, so Andre, what you need to do is to delete the PhD Teach PhD workshop because it's the title of a subfolder I created in my own drive. That's why it doesn't find it. I think you saved yours in the root directory of your drive. So just remove that. It should work. I hope. Okay, if someone gets knows already the shape, okay, good, great. So Zhenshu, that's how you are pronounced correctly. Zhenshu found the shape, so 1,776 patients and 46 features. So yes, that's good that you also look at the question. So here I show you the answer. Actually, yes. Yes, so you have, when you do data df dot shape, gives you the shape of the data set. So with, so it's, it gives you, so first one is the number of rows and second one is the number of columns. So most of the time, yeah, most of the time, correct me, Ronald, if I'm wrong, but most of the time, the patients are in the rows, right? And the features are in columns. Just check maybe with the documentation of a given data set. In this case, it's like this. Yes, and then you can, by doing simply data.df dot head with bracket because it's a function. You can just print the five first rows, and you have a name also of the columns, etc. So yeah, gives you some overview of some values. Yes, exactly. And here, so in bold, here is also the row number. So we see that here that there is no patient ID, it's just a default number. How to get such interactive table? Did you? Oh, maybe I think it's a nice table. It looks nice. And Andre, oh, you get it? Okay. Yeah, the dot head function looks nicer if it's the last line of your cell. Otherwise, it looks a bit weird. Yeah. Okay. So everyone could see that. Okay, so now that we could load the data set, let's look at the feature description. So what I wrote here is just some few lines to make the data dictionary text file a bit nicer. So if you just run the cell, you can look at the table, the list of features, some descriptions that were located in the text file, and the type. So here I split the different features into 3 types: binary, categorical. So both are like categorical, but one with 2 plus, one with more, and numerical. So like age, for instance, or I don't know, yeah, weight. Yeah, so here you have a more, yeah, a better description of what the different variables are. If you have some question about the nature of a variable, maybe Ronald can help you. So as yeah, we also have some blood variables about blood, like hemoglobin, plaquettes, have a units, yeah, heart rate, etc. Okay, so you can observe this for a while if you like. And then so we started answering this, but basically here I wanted to make you a bit think about what different target output features or output labels could you think of predicting. In the case we want to predict some output variables from the patient. Basically in those features, there are a couple of them that we could be interested in predicting. And then, so I would like you to list them and create a table X, data metric X, pandas data matrix that contains only the observable variables, not the output, possibly output variables. So by doing this, I would like you to basically to drop the possible target features, right? And then to create a target variable Y that will correspond to the output label that we decided. So which is sorry, which is day 28. So death within 28 days, which is a binary output, right? So create a Y vector with this, containing this, and the rest drop the other output variables that are super correlated to this output. So I don't know if you are familiar with, if you're not familiar with Python, you may not be familiar with pandas, but it's super useful to load some table data sets. You can it has a lot of functions to play with the features, to play with columns, with rows, to drop, to replace, etc. Similar to our data frame objects. And so one good thing about it is that also you have a lot of software libraries in machine learning, like scikit-learn, which is super popular, that now allows you to take as input a pandas data frame. So you don't need to have a NumPy matrix, but you can keep the pandas data frame with the row names, the patient names, and the column names. And that can help avoid you maybe by mistake inverting some rows or inverting some columns. So that's quite useful. Okay. All right, with X and Y creation, I put here the target variable names that I was thinking of Did you find, do you agree? Did you find something similar? Basically here, what I'm doing is I'm doing a list with all the names that are basically very close to the output clinical variable. Because this is like the number of days spent in ICU. So basically it can give you information. I mean, it's more like an output variable, it's not like a descriptive variable. Here is like the number of days before death. So it's from this you can directly compute whether the patient survived after 28 days, etc. So I listed this possible targeted variables. So we could have been interested in other targeted variables. You can also, in your free time, if you want, redo the whole thing with another target variable. And so target label that we'll focus on here, or at least I will focus on in this answer sheet, is this target label. And to create this data, the X matrix. So I just put this. Basically, I asked to drop those names, those columns in the axis one, so in columns and not in rows. And Y is just, I just take the target label. So then I can also do X and Y shape to check the shape of the data. Basically, so if you're not so familiar with programming yet, I super highly encourage you to print the shape of your data sets very, very frequently to check that you didn't drop something, etc. It can really help you debugging. Okay, what is the difference between target variables and label? Basically, target variables are the set of clinical output variables that we could have selected because in clinical setting, they could all be of interest. And it's just that we will focus on one and disregard the rest. Does it make sense? Yeah, basically, so any variable in the target variable names could be the label. It's just that so that we can all keep the same data set, etc., the same setting. We picked this, but it's arbitrary. Yeah, it's just for this lab session. Okay, sorry, one question. It seems that the target variables are highly correlated with the label. Yes, so exactly, the target variables are highly correlated with the label. That's why we want to drop them, because I mean, this data set gathers both observation variables, like heart rate, etc., and then a couple clinical output variables, like how many days did the patient spend in an intensive care unit, when did he die, etc. And all of them we could be interested in predicting, but we need to separate them. Does it make sense? So that's why here in this line we put drop. Is there any way to identify the good target variables? So actually, I think here it's really it's really here that you cannot do this to me. You cannot do this automatically because it depends on the research question you want to ask. So there's a lot of automatic step in machine learning pipeline, but at some point I think you really need to look at the data set and to think what is relevant, what is really observation, what is really something I can predict. Am I interested in predicting this? So to me here, we really need to read the documentation of a data set to figure out which variables are good target variables. It's a choice that you make. We'll do that later. No problem. Okay. So maybe you can now focus on those few questions. I put you some hints also. So what is the current dimension of X, data X? Actually, I answer that. Count and display the repartition of your target binary output. So the target variables. This is quite some important step that I would advise you to do before starting doing any model. And what comment can you make? So I'll give you a few minutes to think about that. Okay. So any idea about? Okay, did someone manage to find that? What comment can you make? What did you observe? What comment can you make about the repartition of the target output? No hint? No idea? Okay, so I give you some answers. So basically what you can quickly do before we start, I think it's good to look at your target variables to see the repartition. You can use this 0 more. Yeah, exactly. So the label 0, so which means patients who survived after 28 days, there are a much higher proportion than the ones who died. So basically, exactly, Andre. The label 1 is misrepresented. So it means that your dataset is highly imbalanced. it's super common, especially in healthcare data sets, because you're often interested in predicting some disease or rare problem that is not present in majority of the patients. When you want to diagnose, most of the scans you will look at will be normal, but maybe one will have some tumor or some problem. So you need to be able to detect that, even though you have very few positive samples. So that's quite hard. That's quite challenging in many healthcare classification problems. So it makes the classification harder, basically. So yes. So here, by doing this, you can quickly get the percentage of 0 and 1. So more than 84%. Only you have only 15% of true of positive labels. So we have to handle with that. It's a challenge. Okay. 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 Anyone completely lost who needs some help? Everyone's okay? No question so far? Okay. So now we'll do part 2, which is some standard preprocessing steps. So we loaded the dataset. We identified, we split it in like this morning. So X data metrics, observation, and Y target output. But when you see, maybe when we look at things, I think here, we can look at the fact that there are some like nans, which in Python mean not defined missing variable. So you have nans like this. You have some text. You have some like, so here's binary 1 0. Here's some like continuous. So you have something like quite heterogeneous, basically. And this dataset is quite simple in the sense that there are a lot of binary features. It can be much worse, like in some dataset. So how do we handle this? So first thing we need to do is to do some cleaning. So preprocessing, it's not the funniest part, but in practice you will see that you need to spend time on it, and it's an important part before you do all your models. Okay. So first, about cleaning, can you use maybe pandas functions to look at the non-values, so missing values in your data sets X, and what we'll do here, which is not we can do things very differently, but what we'll do it, because we won't spend too much time on preprocessing, etc., even though it's very important for this, we'll just drop the rows that contain non values. So yeah, maybe you can try to use pandas functions to drop missing values. And after that, check again the shape of your new data set. So Andre says he finds final shape 1068.46. So let's check that. So here I put using .no is null. I can see how many missing values are there in each for each feature, and there is no missing value in the target output, which is good. And when we do drop, oh, you still have 46. Andre, did you drop the other target variables? Ah, it's okay. You can work on this one if you like. But yes, indeed, about it drops quite some patients by doing that. So in practice, you have other alternatives to do that. You can, instead of dropping, you can, for instance, fill the missing values with some arbitrary label. So then it can depend on the nature of the feature. I don't know, maybe if you have a missing heart rate, heartbeat, you can maybe replace the missing value by the average normal heartbeat, something like that. So you can replace by, or you can replace by the average within your data set. Stuff like that. Plan some techniques. Can we slow down? Okay, sure. Sure. So here's about here can this code that can help you checking the nans. So basically, when you present is null, I think it will give you as output the whole table with true and false, whether it's a nan or not. So then you can sum. So when you sum, I think it's summed by rows, something like that. No, it must sum by, I don't remember. Must sum by columns. And then I just ask him to ask the code to print only the features that do have missing values, because most of them have no missing values. You see, you don't have all the features here. Okay. All right, Yingli. Yeah, no problem. Do not hesitate to tell me whether you missed something. Okay. And now, so now you need to, when we drop the nans for the x, so here's just some tricks. So you drop on the lines with nans, okay? So that's the drop NR function. But then you also need to keep in mind that you need to also drop your y output feature label. You need to also remove a patient where you have no more observation for, right? So that's why you put, so in pandas, you put .elock. So .lock in pandas means select these rows. But depending, .lock, you need to put the index name. So patient 1, patient 2, patient A, or patient with a unique identifier. Or you put ilock. So ilock, you put just 0, 1, just the number of a row. So here we take the index of X and we ask it to select the same patients, basically. So that's quite convenient with pandas to do this kind of stuff. Okay. So I'll move a bit forward. Let me know if you need more time. Okay, I wanted here to speak a little bit about the machine learning model of input type that I required, because machine learning models, I mean, most of the time, or always, not always require only numeric input variables. You cannot put like I mean, machine learning models in classification, okay, only can handle numeric input variable. I mean, that's only what I can think of. Oh, sorry. I didn't understand about x.index. So if you take x.index, basically, x.index will show you what are the index numbers. So if you do x.head, yeah, because we drop the nans. So for instance, like patient number 1 got dropped. And if you took x.index, it will give you those numbers in bold here. So you just want to get those numbers and to select in Y the same numbers. You have already modified X, or X doesn't have information about rows with nans. Yes. So in X here we drop nans. Is that okay? We drop nans here, so we have some missing patients that were contain nines. Here it's the row number. You just keep the same row number. But yes, the idea is that in X and Y, it's the same order of patients. It has to be matched. Each row needs to correspond to the right patient. Otherwise, it doesn't work. So yeah, here actually in this data set, there is no patient number, no patient ID. So pandas put as default the row number as the name of each row. Does that answer your question? Because in Y, if you look at Y, you have also the row number. I'm not sure I'm clear. The idea with the data frame is that we had a full data set. So drop nan doesn't erase the row numbers. No, yes, by default, it will not reset new numbers 0, 1, etc. I think it has an option to do that. But here we don't want to, we'd like to keep the row numbers. Okay, good. Okay, just remove that. Okay. So following on our input problem, so we need to have only numeric input variables, okay? But as you could see in here, sorry. See here, for instance, we had some features like day ICU in time, so the day where the patient entered in ICU. It's a day name, right? We have some problems like that, right? So how do we deal with that? Here, service unit, it's a name. So we need to encode this so that the model can understand it, basically. Okay, so for instance, yeah, days ICU time, week numbers. So what we can do is ordinal encoding. Basically, for the weekdays, we can do Monday, day 1, Tuesday, day 2, etc. But it can be quite inadequate for some categorical variables where there is no relationship. For instance, weekdays, I mean, here it's not super relevant, but more compelling examples may be gender, or it can be, sorry. Here there is not, but maybe if you have, I don't know, eye color or hair color, or I don't know, it does not make any sense to say, okay, blue eyes is 1, brown eyes is 2. It doesn't make sense. It's a pure convention, right? So here in the data set, gender is encoded, male is encoded as 1, female as 0. It's a pure convention. Okay. But if we keep like this in the model can consider there is a hierarchical relationship between like here male, female, or blue and brown eyes, which is not really what we want to, the information we want to give, right? So to solve this, we can use one-hot encoding. So it's quite a simple and popular technique to deal with categorical feature. So the idea is to take each, for instance, each feature that has a categorical, which is categorical, for instance, weekdays, and then to turn it into dummy variables. So for instance, it will be weekday Monday, weekday Tuesday, weekday Wednesday, etc. So you have 7 different variables instead of 1. And each variable will be binary, either 0 or 1 if it's a Monday. Monday will be 1 and the rest will be 0. So it's quite something we can, that is quite used in practice. However, it artificially increases the number of features, which is sometimes can cause sometimes some problems. So yeah. So here, what I would like you to try is to perform one-hot encoding on categorical features that are not binary. Because when it's binary, it's already 0 or 1, so it's okay. And to do that, you can use pandas get the mix function. And after, you can check again the shape of your new data set, because it will change not the number of patients this time, but the number of features. Okay, if someone has already the shape of a new data set, can put it in the chat. Okay. Okay, new shape. So same number of patients, 1064 and 51 features. Let's see what I found. Okay. The target variables. Yeah. Target variable names. Sure. So this is for to encode categorical features with one-hot encoding. This is how I did that. Basically, I had to list the categorical features. So I list all the, I took the data dict indication to check whether the feature were categorical or not, and if it were also not binary, right? And then I do get the miss of X for both columns, and I get this, right? So I take, as input, I have 48 features. Hope you agree with me at this point. Oh, 47. One left. Oops. Why you have 48? Weird. I can list here the X columns. So for instance, here you can see that by using get dummies, the day ICU in time will be turned as I just explained into seven different features, binary features. Here for service, there was 3 different possibilities, so 3 features. Gender new, also 2 features. So it removes any hierarchical ordinal relationship. Okay. So any idea, Andre, if I missed something, or if why do we have one features difference? And so in our case here, there's not too many features that are categorical, and also when they are categorical, there are not too many possibilities. The one with the highest number of possibilities is the weekday with 7. But sometimes can happen you have multiple possible categories. So then it adds a lot of features. Okay. So here I end with 48 features. Let me know if there is a problem. The first 2 categorical select. Ah, okay. Okay, so we found same. Okay. And then now some preprocessing step, basic preprocessing step is the implementation of what Ronald explained to you, which is the split train val test, train validation test set. So what I would like you to try is to use scikit-learn train test split function to split the data set into a training and a testing set with a proportion 2/3, 1/3. Okay. And I'm not sure adding a new random set is necessary because we set up seed at the beginning, but I don't know, it's just some habits I have. And so I would like you to use this function to do this. And maybe you can look online at the documentation of this function because there is some option you can change to ensure that the proportion of 1 and 0 labels in train and test is similar. Because here we have a quite small data set for machine learning. We don't want, for instance, I don't know, it was 15% of one label. So we don't want like 20% one label in train and maybe only 12 or 10% in test. We would like the train and test dataset to be quite similar. Yeah, that's a challenge also in healthcare data sets, is that sometimes you want to apply is that sometimes you want to use a new data set from a new hospital, for instance, as a test set. but this dataset will be quite different from yours because you have some batch effect, etc. So for designing your model, it's good to try to have a good representation of the data available in both your train and your test. That's better. Okay. So for the break, let me see. So I can give you this. We can just finish this and then take a break. Is that okay with you? Sorry. So yes, so to use scikit-learn, that's the way you can use it. So you need to import this function, train test split. And then you just do a xtrain, xtest, ytrain, ytest. And if you want, oh, sorry, I changed stuff. Yeah, sorry, I put a test size of 20% instead of 1/3. And when I put stratify equal y, means that I want on the y label that it a good split in train and test. Okay. And then what I do next, so I do a train test split. And then what I do after that is, what did I do? A bit weird what I did. Anyway, so I do first train and test, and then the train I split it in train and validation, basically. This was just to save it for reproducibility, but you don't need to do that. And the last one I did, it's for the part 3. So what I propose you is that I stop here, we take a break, and we come back for the next parts, right? I can keep sharing my screen if you want. Yeah, sorry, I did a mistake in the question. Here, by saying test size is 0.2 means 20% of the dataset will be for test and 80% for train. Okay. So is it okay we take a break now? For how long, Ronald? What do you think? How long break?
Okay. How about we can back at 3:15? How about that?
3:15?
Yeah. Or is it too long?
3:20 maybe?
Yeah, sure.
They
Should be no
deserved
problem.
it.
Yeah.
Okay, so let's take a break. Let's come back at 3:20 p.m. Okay. Yeah, sure. You can have your question, Andre. You can ask any question during the break. And for the rest of you, let's come back at 3:20. So Andre, basically, I think I did that because I observed that when I applied directly get dummies, it took also the binary features, and from what I remember, and separate the binary features into 2 features. So for instance, let's say, this like Renault flag, it was split into Renault flag 0 and Renault flag 1, which is not super interesting, right? So it created even more features where it was not needed. I think by default, it's applying one hot encoding to both binary and categorical. Does it answer your question? Okay. Okay, good. See you in a short while. All right. Is everyone back? Any questions to start with before we proceed to the next part? Okay. So maybe to an important point to recall, to mention, is that you really need to keep your test dataset for the end. Because it's very tempting to use it to fine-tune your model. And if you do that too much, you will tend to overfit. So that's why there are some settings like in some machine learning competitions where the test set is hidden from the competitors, for instance. And yeah, sometimes also in some labs with your supervisor, you can ask him to keep like some part of the data set so that you're sure you won't touch it in order not to overfit too much. So that's a big problem. Okay, maybe so something, I don't know if I had time to introduce that. Yeah, here I just created some extra variables, extrain val. Basically, I just concatenated the training and validation sets. That because we'll use that yeah, in part 3, and also dataset train val. So it's my own like choice. Here I concatenate the observation and the target output. So I have a pair of observation output. It's more for the visualization part. Okay. So now let's start part 3, visualization and feature engineering. So actually in this part, it will be more like to show you what different things you can do, but will not focus too much on it because it's not the gist of the workshop. However, I really want to insist on the fact that in practice, it's where you spend the most of a bigger amount of time, because basically now today implementing machine learning models, it's quite easy because the libraries are well developed, well maintained with lots of documentation, etc. So you can do those like model thing that we introduced this morning quite easily actually. But what is very hard to do is to really do the feature engineering. So to arrange your variable, to correct your variable, to do some combination of variable. This you have to do it for every new data set. And it can take a lot of time to clean, to arrange everything. And it will really change your model performances. So here we decided to just show you, give you some hint of what you can do, but we won't like change the data set too much. This will result in very models that will have a poor accuracy, but in your free time, if you're interested, if you want to try, you can spend a bit more time on it. Also, for those of you who have already a lot of experience, you can maybe edit do feature engineering on your Collab on this data set to be able then to give a much better performance than what we will get here. Okay. Okay. So yeah, in practice, this part you spend 80% of your time on it. Okay. So data visualization here, I think we did that already. Okay. First, one big visualization that we can do is the principal component analysis. So we didn't introduce that in the morning lectures because it was not the gist of the workshop. But I guess most of you must be quite familiar with it, even from the medical field of view, medical point. If someone needs is completely lost, maybe you can say it in the chat so that I can explain it. Otherwise, here I wanted to provide you some code using scikit-learn to do principal component analysis on your data set. So first you need to import this pipeline standard scaler, which will help you to standardize variables, and PCA for principal component analysis. And here, what you would do is create a scikit-learn pipeline, which will consist of 2 steps. First is to apply standardization. And second one is to do principal component analysis decomposition. Okay. Once you created this object, you can fit it to your X-train plus validation. So here, the idea is that X-train validation is the dataset you can use for training your models. You don't touch the test set, but train validation, you can play with it. So here we want to look at to fit the principal component analysis on the train validation and transform the data set. So to decompose the data set into the PCA. So basically to project the data set on the directions of highest variance. And because our data set has, as we saw, more than 40 features. So it's not easy to plot it like I did this morning with 2 features only. You can plot it in 2 dimensions. It's easy. Here it's not very straightforward. So if you do PCA, you can summarize your data basically. So here then I just use some panda data frame to reshape the results. And okay. Okay, I create this item. So it's just like some code. And then I use Seaborn to do a scatter plot. And here's the result. Okay. So the idea is that I plot here the data set that I project on depending on the first principal component and the second principal component. Okay. And then I decided to color the H dot. So H dot represents a patient depending on their output variable. So Y, okay. So basically by doing this, I'm coming back to what we saw this morning, like plotting 2 features. It's just that there is much more features that are not represented here, but I try to put a linear combination of features, okay. Basically, this principal component analysis step, it can be quite useful because sometimes in healthcare data sets, you can quickly find some interesting things about your data by just looking at the principal component analysis. You can find some groups, some clusters. You can find outliers that you may want to remove. etc. So it's a good first step to look at. Here, I just wanted to show if there was some interesting pattern or very huge outlier. We can see two main groups. However, I did quite some tests to look at what it was representing. So we see that it's not, it does not do any cluster depending on the target output variable that we are interested in. Okay. So then what I did is that I was quite a bit curious and I wanted to see whether there was one variable in the data set that could explain those two like butterfly wings. Maybe, I don't know, the gender, maybe, I don't know, some medication or some liver feature, etc. So that's why I did this. I did this for loop to create a similar plot, but changing the colorization of the patients here. Okay. And so when I do this, I get kinds of many plots. Okay. And so for instance, each of them, for instance, here I look at, I don't know what it represents, stroke flag. And I want to see how are the stroke flag patients represented in this, in the principal component analysis. But what I saw basically is that there is not a good trend. Yeah, I was expecting some flag to like be grouped, for some flag that all the patient will be grouped somewhere, all the positive patient will be grouped somewhere, but it doesn't seem that straightforward. So yeah, I mean, at least I like it because I think it's very pretty, but sometimes in some settings, it can help you better understand your data set and realize, oh, maybe I should, yeah, this feature is very important, or this patient is a big outlier. So yeah, sodium, potassium, don't see a clear trend. Okay. So we can do this. Okay. So PCA here on this data set was not so useful, but in general, I could advise you to try it to better understand the new data sets. Okay, any question on that? Okay, and maybe the next thing, what is the X-train bar shape? So let's check that. X-train bar shape. This one, 851 patients. So it's a subset of the whole X matrix. Oh, you have 100. Oh, that's very few. Did you concatenate the train? Yeah, show your splits, sure. Okay, let's go back. So here was the split. So first it's not super great code, sorry. But first I split X and Y into train and test. And after that, I split X-train again, so 80% of the data set into train and test, and train and validation. So I think 100, this one you get, right? So I think you have only the validation set. And what I did here is X-train validation. I concatenate both X-train and validation for visualization. X-train and validation splits, it will be useful for the model training. Not so much for feature engineering or visualization. Does it make sense? Okay, good. So I think this code was it's provided in your Collab as well, right? I don't remember. I don't think it was blank cells. And the last, another one, so also it's just for your knowledge, in practice, there is an algorithm which, so I didn't put the reference, has been developed, I think, by Microsoft, visualization algorithm called UMAP, which is very popular, and you can see it, it's used in a lot of papers that deal with biomedical data in order to project your data sets, and can be so a good way to also project your data set. So I just tried it, but again, by coloring the data set depending on the target approvable, I can see a huge clusters forming. So applying those algorithms is not sufficient to separate the data into our two classes. Okay. So far, so good. No questions. So this is more like stuff you can use for new data sets. You can think of using, or if you look at some papers in biomedical data, in biomedical field, you can see a lot of plots like this. So yes. Okay, so then there's summary statistics. So yeah, all this code, you have it, right? It's not blank. I think so. Okay, so basically, yeah, code is Jack. Okay, cool. So here then there's some summary statistics that you can do. So to describe each variable, each feature, to see the range of the features, etc. So you can run those cells in order to see some histograms. So the thing is that you have a lot of binary features in the dataset, but you can see how imbalanced it can be depending on some features. Okay. So here's mostly to see the imbalance. Okay. Then for the continuous variables, you can do some box plots to look at outliers, to look at the shape, etc. So yeah, that can be also useful, or that can give you hints for the feature engineering step that we won't go into details here. But that can give you hints because, for instance, this variable, I put it on the side because the range is super different. So maybe you can, instead of having this, you can try out some transformation of the features. Maybe for some features, it's more relevant to put the logarithm of the feature, etc. Some features that can be good to combine, stuff like that. For instance, here you have a BMI, so it's good, but body mass index, but it will be correlated with the weight, maybe. So maybe it's more useful to have the height and the weight of the patient separated. So you can think of a feature that both make sense in terms of domain knowledge and both in terms of computing, like range of features, etc. Yeah. Okay. And then, so there is the correlation between variables. So it was a question from Andre before. So one of the first things also we can do once we cleared a bit the data set is to look at feature correlation, because some features can be super highly correlated between each other, and then it's not necessarily a super good setting for the model, for model training. So sometimes if you have two correlated features, maybe you can drop one of if you have two correlated features, you can drop one, and it can result in better results. So here I just provide you some code to plot correlation matrix. Okay. So maybe some comments we can make. For instance, here it was the encoded variables. You see that for the service, for instance, there are some features that are super negatively correlated, for instance, because I think, where is it? I think it was gender. Yeah. For instance, if you have gender num0, which is, I think, female, and gender num1, which is, I think, male. So you see, if you correlated basically gender male and gender female, it's negatively correlated. So it makes sense. If it's not a male, it's a female, right? So you can think you can look at some things like that. Also here, like weekdays are negatively correlated, because if one is 1, the rest will be 0. So they move in opposite directions. And basically, there are maybe some features. Yeah, for instance, here we see BMI, body mass index, and weight first, super correlated, as we could expect. So here you can see if there are features that are too correlated together. So depends on your data set, but sometimes you can have way more features, and you can drop maybe half of them because they are too correlated with each other, with like a correlation coefficient of more than 80%. So then you can get less features. Okay. So this was between variables to see how they are correlated. Then you can also look at linear correlation between each feature and the output variable. Okay, so it's some code. You can run the cells also on your Collab. So here's the range of a correlation between -1 and 1. And you can see, I don't know, if someone has some comments to make, please feel free. But yeah, maybe you can see that, so the target label, let's recall that it's the survival label. So yeah, maybe what does it mean? Mean that the less BMI you have, the more likely you get, the more likely you can survive after 28 days. I guess it depends also on the BMI. Maybe when patients are suffer from obesity, it can prevent them it can lower the chance to survive in ICU, something like that. So you can look at some, can be interesting to look at some features. What is the difference between core and core with? A core in pandas data frame, when you score, it computes the correlation between each within the matrix. So it considers each column as a variable and computes the correlation of two sets of variables within this matrix. While a core with will compute the correlation between one variable or one set of variable and another target variable. Does it make sense? Okay, cool. Okay. So yeah, this part was basically more to give you more insight of what kind of job you can make and you can expect when you have a new healthcare data set to analyze. So maybe because we're a bit lazy, we didn't do it fully, but it's something you can experience. Have here some code to give you some hints about variable modification you can perform. And now we'll focus on the model implementation. Any questions on this part so far? Okay, so let's look at part 4, classifier implementation. So in this part, the goal is to try to implement using well-known libraries the models we discussed this morning. So first question I would like about logistic regression. So I would like you to implement a logistic regression model to predict target Y from observation data X. And to do so, I would like you can get inspired of the quote from PCA to create a model pipeline using scikit-learn that performs data normalization plus logistic regression with default parameters, hyperparameters. Okay. So I would like you to create this object, this pipeline object, and then once you created it, to fit the pipeline, so the model, to your training data, and to evaluate it on your validation data. Okay, so here we are implementing classifiers, so we don't look at the test set yet. We just try, we take a little bit of the training and validation. Okay. And to evaluate it, I would like you to use some metrics. So we didn't introduce fully metrics, evaluation metrics yet. We'll do it more in details tomorrow, if I'm not mistaken, Ronald, right?
Sorry?
For the metrics, we'll see it more in details tomorrow, right?
Yes.
Yeah.
Yes.
Yeah, so it's just you can use ROC AUC score, or if you are more familiar with like accuracy, you can use accuracy to compare the output prediction and the ground truth. So maybe you can give you a few minutes to look at that, right? You can, so I could, if you've never seen like scikit-learn before, I can encourage you to look online at the scikit-learn pipeline, scikit-learn logistic regression documentation. And if you have some questions, maybe we can give like 5 minutes to think about it, right? And then we'll come back with the answer. Yeah, we're doing part 4. I just wanted to give you some time to think about the logistic regression implementation using scikit-learn functions. No problem. If you have questions also about this to answer this problem, you can ask. It's just that for the rest of the models, basically, it will be quite similar to this first question, because scikit-learn is well designed, and it uses basically the same shape, can use the same pipeline, just have to change the model in order to train a different model, but the code, most of the code will keep the same. All right, so do you want a bit more time, or do you want me to share the answer? 2 minutes? Okay, sure, no problem. All right. Did some of you manage to do that? Do you have some questions about it before we just look at the answer? Some things that doesn't seem to work? Ready for the answer, or some more time, as you wish? After I use .fit, how can I use? So to do that, so when you use .fit, basically it does the training. So what we saw this morning, it estimates the parameter, but then to use AUC score, maybe you need first to compute the a prediction. So I guess you use .fit with your training data. So then you can use this train model to predict output of on your validation data. And then you can compare the predicted output and the ground truth of your validation data to use AUC score, using AUC score. We can spend some more time thinking on it because really once you understand how to code one model, then for the other models it's quite simple thanks to scikit-learn library. So you have input shape issue. What did you put as your input? It looks like you have only 2 features as inputs. Oh, maybe there is maybe I did a mistake because when I did the principal component analysis, let me see. I think did you take as input the principal components only? Because it looks like, Andre, from what you're saying, you have 1,068 patients as input and 2 as output. No, the whole X-train val. And so when you take X-train val dot shape, it gives you this. Weird. I think there must be an issue with that. So X-train val, so here that means you took X actually, right? Yeah, so you took the whole X, you took also the testing set. Okay, so normally you should not take your testing set at this point. Only the X-train val, right? To reserve some samples from the testing, final testing. Oh, did you manage? Okay. Okay, hope you managed to solve that. Oh, you have some AUC score. Nice. Let's look. Let's look at what I wrote. Nice. What did I? Oops, not exactly the same. So this is the few line codes you would need to create a logistic regression model. So you see, thanks to this library, the whole complicated principles I could explain this morning basically can be implemented in a few lines. So that's nice. So you need to get those imports. Then to create a pipeline similar to the principal component analysis before. Oh, maybe it's because I did not put the, oops. I think I did not put the normalization. Did you put normalization, Andre? Yep, okay. I think I did that. Okay. Yeah, maybe that can explain the change. Let's try. Scalar, standards, scalar. Did you specify the random state? No, I'm not sure it's needed actually. Let's try that. Oops. Okay, AUC. Oh, weird. Still have no, not the same one. Oh, and as input, you put X-train or X-train val? Did you fit on X-train or X-train val? X-train to fit. Oh, weird. Okay. Xval to calculate, yeah, AUC, same. This is I don't know why it's not exactly the same. Should be. Sorry for that. Metric and rook NUC. You mean it's a code? Oh, you have a code. Okay, thanks. What seems correct? So it's not the same. Weird. Could you just give me the shape of exchange X val, please? Okay. Yes, looks same. Weird. Why do I have that? Okay, sorry for that. Maybe I missed some seed thing or whatever. Okay, sorry for that. Right now I cannot really tell why there is a difference in score. However, I hope you can understand just practically how to run the code. So here for your, if you want, you can also, in addition to AUC score, you can also compute the accuracy and F1 score. It's metrics that we will explain, that Ronald will explain you more details tomorrow. Oh, I get same, right? I get same as Zheng Xi. Sure. Sorry, pronunciation. Zheng Shi. Okay. Okay, maybe I can look back at and trades code later. Ah, there is some issue. Okay, let's hope you can think that you can solve that. And maybe, yes, so something that is quite useful also that we'll see more in details tomorrow is the confusion matrix. So basically, when you have one score like this, sometimes it's a bit hard to visualize what your model is doing. So one thing you can do is to use a confusion matrix. Basically, you have a predicted a truth label 0 and 1 and predicted label 0 and 1. So it's very useful in binary classification. And ideally, for your confusion matrix, you would like this diagonal to be dark blue, because you would like zeros to be predicted as zeros and 1 to be predicted as 1. And the rest of it is like misclassified samples, right? And here we have, in addition, the issue of the unbalanced problem dataset. So it makes it hard to detect the one, right? Oh, yes. It looks like you have the same as my demo code. Cool. Hope you could figure out, understand. Ah, you use predict probat instead of predicts. Okay. Okay. This we can remove. This you don't need to, it's just for Ronald and me. Just some code to save your model and to reload it back can be useful sometimes. So to once you once you train the model, you want to keep it in order to reuse it in other settings. You can keep it on your desktop, etc. So you can use Pickle to do that. So you can write a Pickle file, which it enables you to write class objects like scikit-learn models. So quite useful, but you don't need that here. Okay, so basically now that you've seen that, I would like you to try to do something similar, but with supervector machine. You're lucky you have supervector machine implemented in scikit-learn. So let's try to do that. So the last block before exam, you don't have to write it. It's just some logistic, some convenient block to save a trained model into a file, a pickle file, to be able to reload it again and to share it with other teammates, for instance. But here you don't need to save it. It was just between Ronald and me. The Pickle module allows you to read and write class objects into files. Yeah. So I can give you also a few minutes for SVM. Let's notice that the code is very similar from what we just saw. And but using, I have to change the model type here. So you can look online on scikit-learn to do supervector machine classification. Okay, does anyone has already the ROC AUC score for supervector machine? Okay, 正式. Okay, with linear kernel, 0.74. Okay, so let's look at that. Oh yeah, I already put some stuff. Sorry. Yeah, already tried to improve. Okay, so default one. Default one. Did you do normalization before? Yes. Weird. SVC. You put kernel. Okay, sorry. Kernel. Yeah. Okay, so I get same as you. when I use linear SVM. Here again, and here you can look at the confusion matrix, which is actually quite close. If you have default parameters, like quite close as the logistic regression, and not very good. Not a great model yet. So it's also, it gives you maybe a practical sense also on how important it can be when you have a new research project in healthcare. You want to acquire data. You really would like to get some balanced data sets. If you're interested, for instance, of a set of disease, it's really, really helpful when you have, usually it's not possible to do so, but if you can, it's really better to try to have a similar number of samples between each class, each disease or each category. Okay. You need more time, or can I proceed? No questions? Okay. Let me know if you want to read the code cells that were above. And finally, let's try to implement the last model that we saw today, which is k-nearest neighbors. So also that's very convenient because scikit-learn provides it for us. You have same score, cool. Okay, so now let's try to look at the last model, k-nearest neighbors with default parameters, and yeah, you can post the AUC score that you get with that. Okay, does anyone manage to get some score for KNN, k-nearest neighbors? No score? The last one. Give you some hint. Give you some code here. So you see basically that once you get familiar with the scikit-learn library, you can very easily build new models, changing the pipelines, adding some other step and just normalization, or can be it's quite very convenient for that. Okay, I have some scores. 0.57. Yes, that's what I get as well. And here's the confusion matrix, which is even worse when that we have what we had before with two other models. Okay, good. So basically here, the goal was just to learn how to write those codes in practice. What are the standard parameters for STNs? So here you need to look on it. Sorry, I don't know it by heart. Okay, and then classifier. By default is 5 neighbors, right? Then you have also by default, so you have weight uniform. Then there is algorithm. The metric default is Minkowski. So basically, let me see. When it's p equal to, it's equivalent to Euclidean distance. Yeah. So it's very convenient, those functions, but yes, it's also very important for you to really look at the documentation, because so many parameters that are set by default, usually they are well picked, but you will see later that there are also some code we can do to try to pick the best hyperparameters for our a given setting, right? So by default, 5 neighbors. Okay. Okay. And I think, if I'm not mistaken, it's one of the last thing of our, just let me look at something. Don't want to show you all the rest. Okay. So I think now the last exercise we can do for today is to try to find the right parameter k. Okay. So that's what I ask you to do in the next question. Because for KNN, the K parameter is really the big hyperparameter to set. So what I propose you to do is to plot the classification accuracy and fit time, if you like, according to the number of neighbors K. Maybe you can focus on the classification accuracy, okay? Plot the classification accuracy, so you can do a for loop to train different models with different K parameters. And then based on the plot you get, try to pick a good K. Is the question clear? Why is KNA so bad? So it's to me, what may miss here is that we didn't do a parameter feature engineering. And so I think there are a lot of different features with different range because of different units. And even though we normalize it, I'm not sure they are well spread. The distribution is like equal between and the feature weight is equal between each of them. And this is something which is quite important for KNN in general, so that can be a reason. And also we didn't, we pick a random K, so that can also explain why it's quite bad. But yeah, I mean, many different other hyperparameters can interfere because, for instance, maybe the distance metric that we use also is not adapted, something like that. So that's why, like in practice, normally you should iterate through all hyperparameters possible. I mean, not all possible, but a good amount in order to make sure that your parameters are well suited to your example. With k equal 3, you have 0.62. Let's see. Okay, interesting. To me, so this is the plot I get when I put the validation error rate depending on k, number of neighbors, and I find kind of like a minimum at k equal 9. Okay, interesting. Do you have, I was wondering, is your error rate based on the validation or on the training set? Okay. Okay, using exam, so it makes sense. Interesting. You did standardization as well, like standard scalar, right? Oh, you put AUC. Yeah, I put AUC as well. Error rate, score. Oh, and you put AUC. Here on here, I think maybe something that can affect what you see is that AUC rock like that. No, say rock AUC, right? Okay. Error rate, I put 1 minus accuracy. Maybe that's why we don't have exactly the same thing. AUC plot is unstable. Oh, okay. Something I did also is that I took only odd numbers as a number of neighbors, as because we're in binary classification, we have two classes. By taking only odd numbers as number of neighbors, then I don't have the problem of like having for majority voting of having two neighbors green and two neighbors blue. Maybe that can explain why your plot is a bit unstable. Maybe the error rate increases a bit when it's even number. But then the idea of this plot is to then help you pick a better parameter k. So in my case, so I hope you'll be able to reproduce, or if I did a mistake, to let me know what's wrong. But to find some minimum, also good for a good trade-off. So here to select k equal 9, and then to pick that for the rest of the for your model, right? So once you have that, you pick k equal 9, and you can do the exact same, copy the exact same code as before, but what I called KNN fine-tuned, which is then with a well-picked, well-selected number of neighbors, right? Did it change something actually? 57. No, actually, it doesn't change that much. On this dataset, to be honest, it's not super striking. The dataset is also small. I've seen cases where with KNN you can see a much smoother curve with some elbow, and then you can pick. You have a few choices for your K. Interesting here, 5. Yeah, it's even worse. It's even worse. Yeah, and so this was the last thing I wanted to look at today. And tomorrow we'll focus again on the same document, but for with the rest of the cells. You can play with it if you like. Yes, sure. You mean the recording, oral recording, or the answers? According to error rate, k equal 9 is the best. Cool. Yes, recording. So recording, maybe we can ask Sam, right? Ronald.
Yeah, for the recording, needs to check with Sam.
Okay, and
we'll inform you
maybe
later.
yeah, maybe for the answers, what I can do is to create another document with only the answers for today. Share it with you, right? Yeah, no problem. Okay. Okay. So to me, today I'm done with today's tutorial. Any question? Any last questions? So we'll try to share the workshop answers for day 1 in the recording. Okay, nice. You're welcome. let us know if you have some last answer before leaving the workshop. Okay, nice. So then see you tomorrow, right? For the next, yeah, for the following session. We'll focus on multiple layer perceptron and metrics evaluation, model evaluation.
Model evaluation metrics.
Okay, nice. So see you. Thank you very much for all your questions. I think we can use AUC score. I just, to be honest, I think I can use. I think I just got inspired by someone else's code because basically, if you have the AUC score, then you want to maximize it. And here I wanted to show, according to my side, I wanted to show a minimization of the error rates. Just you can use either way, but if you use the AUC score, then you want the K that maximizes the AUC. Looks unstable. Okay. Not quite sure why. Yeah, sorry, not so sure, Andre, about why it's more unstable. Did you take only odd case? Maybe you want to try with only odd case. Because I'm not sure I remember well, but I think I tried with all case, and with even case it was it used to do some like peaks. I can try maybe here. I take. Yeah, you see, when I don't take odd case, then I take, then it's more unstable. Does it make sense? Is it because we can? Actually, RoKUC is quite popular because even if your data set is imbalanced, RoKUC will give you 0. The default threshold for RoKUC is always 0.5, even though your dataset is unbalanced. That's for sure. I'm not sure whether this can cause this instability. Quite unsure. But even with odd k, the max corresponding to small k. I'm not sure I understand your sentence. So the AUC score, you mean? Oh, AUC is the blue line for me. Does it look like yours? Yeah, and even with odd ones, let's look. Oh, I see. Yeah, why that? Yeah, interesting. Not so sure why. Maybe I can try to think about it. Not so sure why. I just saw most of the time, like online in tutorials and books, that people use the error rate instead of the AUC score to do this plot. So I'm not quite sure. Oh, you mean here, even with error rate here, it's, no, it's high, right? Yeah, I'm not quite sure. Not quite sure. Yeah, error rate is okay. Not quite sure for AUC, to be honest. Yeah, if I find the answer by tomorrow, I'll let you know. All right, any more questions? No? Okay, so otherwise, yeah, enjoy the rest of your day, and we'll try to come back to you with answer sheet and recording. Thank you for your attention and participation. See you tomorrow. Bye.